In Lesson 6.3, we're going to talk about something called a logarithm, and we're also going to use them to evaluate exponential functions that we worked on in Lesson 6.1. So we start out in example 1 with a pretty simple idea here. It says 2 times some number makes 8. Well, a lot of us can just know in our head that the answer is 4 from our math skills. But it's important that you show your steps or write down the work. So we would show that we divided by 2 on both sides to get x equals 4. And the right side here, it says 2 to what power makes 8? Well, we know 2 times 2 times 2 makes 8. So we could just say, well, x would be 3. That's because 2 times 2 times 2 is also the same as 2 to the third power. Right at this point, we would accept this type of information as showing your work or explaining your thinking. But sometimes, let's say, for example, 2 to what power makes 17, we could guess, but it's actually not going to be a perfect value. It's not going to be a whole number for our value of x. We need something to help us reverse, if you will, because over here we took 2 times x, so instead of multiplying, we need to divide by 2. In this case, we need something to reverse taking a number to a power, and that's where a logarithm comes in. 2 to some power making 17, we know it's not a perfect number, or a perfect whole number rather. We need something to help us solve this. And that's what we're going to call a logarithmic function. It's the inverse of an exponential function. That means when we want something to be able to say, hey, how do we get this x solved for when it's in the power, as in on the last screen, we know we can take the logarithm of both sides to figure it out. So here's a really important concept, and you'll use this over and over again. You'll notice the color coding that I have going on to help us rewrite any exponential as a logarithmic function or vice versa. I like to refer to this here as our base. This red A is the base before the exponent that's in blue x. Notice over here, though, in logarithmic form, the base is now that little subscript, that little tiny number down below the log, and the power is now outside here as the answer. Think about it this way. If we're talking about an inverse of a function, we learned previously in the first section that the x and y on a function, they switch places when we're finding the inverse. So when we were normally going to input an x value into our exponential, that was our input. Our output is the x on our logarithmic form. That's because an exponential and a logarithmic function are inverses of each other. So we'll also note with this yellow here that when we had our output, our value when we took a number to a power, our output on the exponential is what we put in to our logarithmic equation. So down here on the try it, it said rewrite y equals 8 to the power of x as a logarithmic function or equation. So our base, our pink or our red variable here, our 8, becomes our base in our logarithmic there. Our y, which was the output, is now our input, and the input of the power of x on the exponential becomes the output of the logarithm form. The more you practice these, the easier they'll get, but they're super important to solving. So let's take a look here. I've got on example 2, my base is 3, my power is 4, and my output is 81. If I was going to rewrite this as a logarithmic form, this is our exponential, I would write the log. Remember, this base is our little base of our log. The input 4 becomes my output of 4, and my original output of 81 is there next to my log base 3. Here I would have my base is my 10, my power is my 3, and my final answer is 1,000. I like taking an exponential and writing it as I like taking a log function and writing it as an exponential because it's a lot easier for me to think about. 10 to the third does equal 1,000, so I know I'm right. Same thing down here. My 4 is my base, my power is 2, my output is 16. And again, one more example. To write this as a logarithmic, we start with log. We put our base in our tiny little subscript there. Our answer is our input now. And then our original input of 3 is there. You could check these on Desmos as well. There's a little button under functions. It says log little a. You can use that button. Not every calculator has it, but on Desmos, it's on the functions tab under miscellaneous, and you'll find this button. Ask your teacher if you need help finding it, that you can actually type log base 7,343 to check if you got it right, and it should equal 3. And so again, more practicing writing them as an exponential. So they ask, what is the value? Like, what does this simplify to? Now, you could type that into Desmos, but let's express it. This is a logarithmic function. Let's express it as its inverse. This is saying, we want to know what this answer is. 5 is my little base. To what power would give me 125? I know that would be 3. So the answer to this value would be 3. If you rewrite these as exponentials, it helps your brain think about them a little bit easier. So our 1/4 is our base. To what power makes 16? Now, you're probably thinking 4 squared makes 16. If I just said this was a 2, that would mean 4 squared makes 16, but somehow I want that 4 to come up to the top in the numerator and be just 16, not 1/16. That's where that negative comes in. Remember, anything to a negative exponent will flip-flop your fraction, or take the reciprocal, that is. Here we have our base is 3. 3 to what power makes 0? We've talked about the graphs before. We've graphed 3 to the x in a previous example. 3 to the x looks like this. It never crosses a y value of 0. It will never equal 0. It has that asymptote. So there is no solution here. And then finally, there's our little base. This one's very entertaining because the answer's right in front of us. It says 2 to what power makes 2 to the 8th? It doesn't make sense for us to multiply out 2 to the 8th power. Think about it. What's missing here if you want it to be 2 to the 8th? That would just be 8. You can try these try-its and check in your answer key to get a little extra practice evaluating those expressions. Now, on a warm-up we've done in class here, we would say that we have all of these tulips have something in common. So we've got our log base 10, log base 10, log base 10. And this one's asking 10 to what power makes 100? Well, we could say that's 2. Or 10 to what power makes 1,000? That'd be our 3. But now 10 to what power makes 500? There isn't a perfect whole number that's going to work. If you were to do this without a calculator, a good guess might be like 1.5. Because think about it. We know 10 squared is 100, and 10 to the third is 1,000. 500 is right in the middle of 100 and 1,000. Or not exactly right in the middle, but between there. So if anyone guessed 1 point something, we'd be correct. Now, we all know our calculator can do this for us, but we wanted to show you that if you're reasoning these, 10 to some power makes 20, this just has to be 1 point something, say 1.2 maybe. You can check those on your calculator for the correct accuracy. But we also wanted to point out that all of these have this base 10. Mathematicians use the base 10 a lot, so much so that we actually just refer to that as it's like the most common log. It's what we call the common log. It's a base 10. Anytime you just see log x, 10 is not written there, but it's implied. So when you saw this example 4 here, we can use the calculator to check, but this is essentially saying we don't see the 10 there, but we could write it in if we wanted to. It's saying 10 to what power makes 900? Kind of resembles those tulip problems. We know it's going to be close to 3, but it's actually going to be 2.9542. Now, I got that from on my calculator hitting the log button. Every calculator has a log button. You don't need to put that base 10 in there because remember, anytime you just type log on a calculator, that button assumes there's a base 10. So these ones you could keep trying as well. There's something extra we wanted to introduce to you. E is also a very common value found in real-world applications mostly, like say half-life or exponential growth and decay. It's 2.71 approximately. It's kind of like the number pi that goes on forever. But again, mathematicians noticed that it was occurring naturally. This ratio was occurring naturally in the world, so they called it a natural log. And they knew they couldn't use this log button anymore, so they used the button that says ln on your calculator. That's an L, not an I. Base E logarithm, this is called. That means if you see natural log of x, it's basically like writing log base E. You could write it like this too. But they used it so often they gave it its own button. So you could try this on your calculator. If you had a little e here, this would be asking e to what power makes e? Because this would be that letter there. Well, this one is a pretty easy one because it's a 1. Natural log of e is always going to be 1. You'll find this one has no solution because just like any 3 to the x exponential, our log graph, it never goes below the x-axis, so it can never have a negative value. I would suggest on the try it, go ahead and make sure you can plug in each of these values to your calculator very carefully, round carefully, and check your answers on the answer key. Finally, for example 5, we're going to use what we were previously doing to solve each of these equations. I'm actually going to start with the try it part A. When it has log of 3x minus 2 equaling 2, first, I want to remember that that's a 10 in there that we don't always have to write, but I'll use it to rewrite this as an exponential. From our previous work on the first example here, we know that this is 10 is our base to the power of 2 equals 3x minus 2. From here, it's just an algebra problem. We have 100 equals 3x minus 2. We're going to add 2 to both sides to get our 3x alone. 102 equals 3x. If we divide by 3, we get 34 for our value of x. If I jump up here to the natural log one, again, remember there's an e there. So this would be e to the 4th power equals 2x plus 3. Now, e to the 4th you would just get from your calculator. But before I go to my calculator, I'm going to get this x all alone. So I'm going to subtract 3, so I'd have e to the 4th minus 3 equals 2x, and finally divide by 2 on both sides. So I would just type this very carefully into my calculator, e to the 4th minus 3 divided by 2. You'll find that e, you can just type an e on Desmos, or it's actually the second ln button. You push the second button and the ln button on your TI calculators to find that. When you do that, you should get a value of approximately 25.799 for x, if I'm rounding to the nearest thousandth. For part A on the try it, so notice how these two examples, my B on the example 5 and my A on the try it, they had log or natural log in them. I rewrote them as exponentials to solve them. Now this one's written like an exponential. I'm going to rewrite it as a log. So since it doesn't have an e involved, it has that base 10. I'll rewrite log base 10 of 25 equals x minus 1. This part I'm going to get from my calculator, but before I do that, I'll know that that's going to be a unit, and I'd add 1 to both sides. So I'd have log of 25 and then add 1. Notice that I'm going to make sure I use parentheses because I don't want to have someone take 25 plus 1 and get 26. By doing this, I would find that my decimal for my calculator says 2.398 for x. Finally, here I have my e. This says e to the power of x plus 2 equals 8. If I rewrite this as a logarithm, I'm going to use that natural log, and I don't have to write the e, but I will. My 8 comes over here, and my x plus 2 is the answer. Remember, this is like your input on this exponential, so it's your output on the log version. Now, I don't have to write the e, so I could write natural log of 8 equals x plus 2. If I wanted to solve for x, I'd subtract 2 from both sides. But note, in my final answer, I want natural log of 8, then minus 2. I don't want someone to take the natural log of 6. And that, with my calculator, comes out to 0.079 if I round to the nearest thousand.